Okay, what I actually thought to talk about was a little bit different to what's in the program. I think the program says the LED lighting revolution. In fact, I'm only going to talk about one small section of that revolution that we have. Perhaps the one that's most relevant to saving energy in the future, and that's lighting class LEDs. White LEDs, you're probably all very familiar with, backlighting in your mobile phone. More and more flat screen TVs or LEDs. You've seen it in cars. So really the white LED is having a huge impact on the way we make light and use light. But what I want to focus on is what are the important steps in actually taking this technology, which is all very well to light up your small display in a telephone, but when you need the amount of light that we have here in the room, then of course you need a slightly different technology. So that's what I'm going to focus on. Very briefly, the overview, talk a little bit about Cree. Cree is one of those companies which very few people have heard about, but we make devices which actually appear in a lot of the things you probably have at home, whether it's your mobile phone, your car, your TV. There's about a 30% chance that they all contain Cree LEDs. So I'll just briefly mention Cree. Then looking at the roadmap for solid-state lighting. You'll hear that more and more in the future, talking about solid-state lighting. The perspective we have today and how quickly it's going to be introduced into society. A little bit of the technology, performance, binning, reliability, what all these mean in terms of choosing the right technology, and then how you might optimize those for different applications. So very briefly, Cree, founded in '87. It's a spin-off from North Carolina State University, and it was started as a material company to make new semiconductor materials, silicon carbide and gallium nitride. And very quickly, the founders discovered that to be able to sell this new material, they had to make devices to show people what you should do with it. And that's where we started making power devices, high-frequency devices, and then lighting devices. And very quickly, that's changed into the dominant part of the company. In fact, lighting products is about 90% of revenues at the moment. Company is growing very quickly. You can see in 2009, we had a revenue of about 560 million. Already during 2010, that had jumped to 860, and that's despite the fact that the world was in recession. So it's growing enormously quickly, and that reflects the importance, particularly of this light-emitting diode technology. But even in power, which is an area I more typically work with, or RF, you have huge implications for saving energy. So the LED technology itself, dividing it up into three different sections. LED chips, I'm not going to talk about, but as I said, it's the thing that probably you have in your laptops or mobile phones or TVs. It's there. Volumes are simply enormous. We sell about 15 million devices per day. So this is not an exotic technology. There's lots of devices being produced. In this talk, I want to focus on these two areas. The areas where you begin to get a lot of power from your LEDs and can make a big impact in lighting and more in the kind of domestic lighting, which is going to be where we save the big energy future. So the Cree Mission sounds like a crusade, but really it's just an excuse to show this nice picture. Lead the LED lighting revolution and make obsolete energy-efficient light bulbs, energy-inefficient light bulbs, sorry. And that's really what it's all about, is replacing a technology which is pretty old now with something which is much more efficient. So, by way of introduction, I wanted to show this. This is the Department of Energy Roadmap from this year, showing a little bit how the technology which is relevant to lighting applications has evolved. Different kinds of lights. When people talk about a cold light or a warm light, this really refers to whether it's a bluish kind of light, which you might use in an office environment, or a yellowish, warmish kind of light, which is more the home environment. And depending on which technology you're looking at, it has a different, what's called efficacy. Efficacy is lumens per watt. It's the human eye perception of light intensity per watt. So clearly, the higher the lumens per watt, the more light intensity you get for a watt of power put into the LED. And of course, for lighting, you want as many lumens per watt as you can get. And over the last 5 or so years, that's the trend for the technology, to be more and more efficient at getting the light out for every watt put in. So, in fact, the progress has been dramatic. It's for warm light and for cool light, it's progressed very fast. And what's particularly interesting is if you look at the roadmap from 2006, it looked a bit like this. So we've actually gone faster than the original roadmap from 2006, and that doesn't happen very often. So in fact, this rapid progress is really why the whole roadmap for introducing LEDs into lighting applications has really accelerated. So what does all this imply? If we look at the different technologies and compare it with the kind of lighting we use today, well, the incandescent bulb is down here. As we all know, it's very inefficient. You get very few lumens for every watt of power you put in. What is interesting is that the supposed low-energy lamp, the compact fluorescent, actually isn't terribly good at all. Okay, it's a lot better than the incandescent, but in terms of lumens per watt, it's still a relatively inefficient technology. If you compare that with the fluorescent tube, we're doing a little bit better, and then the high-intensity discharge, the kind of things that you use in streetlights, is better again. But as you can see, if you look at the technology that's being used in LED production, we've already, from day one, exceeded both the compact fluorescent and the incandescent. And now, in the latest production technology, the XPG, we've even exceeded the high-intensity discharge lamps. So we're, in terms of efficiency, racing ahead. And of course, that's production. When it comes to research, we're actually doing a lot better. So already, the XPG technology was developed about 3 years ago. That's now in production. Next year, we will introduce the XML technology, which has been 2 years since it was developed. And by now, we're already up at over 200 lumens per watt. Compare that with what we're doing today in compact fluorescence. You can begin to get a feel for just how large an impact it's going to have on energy saving. And even things like high-intensity discharge, we're almost twice as efficient. Progress is happening pretty fast. This is looking at this latest generation towards the XPG technology. Now, compare that with the previous technology, you can see for the same amount of current, or rather for the same amount of luminous flux, the same amount of lumens out, the amount of current that's needed, the amount of energy in, has decreased by about 30 or 40%. So all the time, increasing efficiency. The other important thing when it comes to LED technology is to think about, well, how does that efficiency change as we try and get more and more out of the LEDs? And the typical thing that happens as you try to push more and more light intensity out of the LED technology, the number of lumens per watt is decreasing. And again, here you can see the impact of the latest generation. If you compare, for example, at the same efficacy, the same efficiency in terms of lumens per watt, we can now achieve almost 3 times the amount of light out of the LED. Or alternatively, one can think about it as if we maintain efficiency, how much more power, light intensity can we get out? And that's a factor of 5. So all this is changing the situation. We've now reached the point where LEDs become so efficient that they can have a very strong impact on the choice of lighting options. And all this, of course, is very necessary, both from a saving energy perspective, but also from environmental pollution. We want to try to reduce the amount of mercury in the environment. And we've talked about this morning environmental impact, trying to reduce pollutants in the environment. And this is going to be a very big factor in the future of changing technology. So this is an example from Germany where 8 to 10% of total energy consumption goes into street lighting. And of that, over 33% uses mercury vapor. That's over 10 million street lamps. And of course, this is a very undesirable situation. There's a lot of legislation coming in which will change this. The EU is reacting, so from 2015, mercury vapor will not be allowed in street lamps, which is a big, big change. And sodium vapor lamps, these high-intensity discharge lamps, are also being phased out. And you can see all that's going to happen very, very quickly. Over the next 5 years, most of these technologies are going to be phased out in favor of something else. And of course, LEDs is the obvious choice. Not the only choice, but it's clearly what we believe will be the main technology in the future. The other interesting thing, if you remember that first chart, where we're improving efficiency by a factor of 2 or even more, it means that you're going to save, just in Germany, 5% of their total usage of energy today. That's a huge impact. So, all these factors are really going to accelerate the adoption of light-emitting diodes. So if we look at the different applications and the evolution of the technology, where does it all fit in? Well, what's already well established is using light-emitting diodes, things like portable applications. You've probably all got a flash lamp which now has an LED. Architectural, where it's there for things like illuminating towers. Now we're moving into being able to have street lights, replacing these spotlights in your home, garden lights. This is where the current technology is edging in. And now with this next generation, where we're up again in efficiency, we begin to replace the main lighting capability. So what's the focus at Cree? Well, in fact, there are different directions we're taking. When it comes to optimizing the LED technology, there are different things one needs to do. One is talking about brightness, get as many lumens per watt, but that's actually not the only thing that we need to look at. We need to look about coloring. Different applications call for different light color. There are different preferences. Here in Sweden and in the north, we prefer a warmer light. In Asia, they prefer a blue light. So there are all kinds of regional variations. Different applications require different shapes of light, a spot or a distributed. So there are many variations in this development. It's not just a single product, it's a whole family of products. And this is just showing a little bit of the kind of optimization that one needs to do. For example, in parking, if you take that one, roadway parking applications, street lights, the discussion is all about total intensity and efficiency. The actual exact color of the lighting is really not important at all. Whereas for other applications, it's the color of the light, which is the important thing. The actual intensity or the reliability is less important. So again, it's not a single problem, it's multiple problems. And for multiple problems, you have multiple products. Some of them are very large, some of them small, depending on exactly how much intensity one needs from each device. So we've spoken about efficiency. The other thing that we optimize is color. And again, this was back from 2006, where we were just starting all this. And at that time, there's the ANSI standard, which defines different color temperatures for a light source. And the red squares show at that time how the LED technology was arranged so that the selection you did was within each of these different boxes. Fast forward to today, and now you can see that there's a much tighter control. You're meeting the ANSI standards very well. So this is from one supplier. Other suppliers have gone a step further. So now they have even tighter selection criteria. And I'll come back to why that's important in a moment. Other suppliers have chosen to focus, and supplier D is doing it all together. So to date, the LED suppliers are responding to this requirement for different colors and really advancing the technology. There's something we call EasyWhite. Two different strategies here. One can make the absolute best selection, but if you do that, then of course you're looking at a small percentage of your total yield, and that can be expensive. Another way to do that is in your fixture. You mix from different capabilities to blend the right white that you need for different applications. It all seems like a lot of details, but it's amazing how important this is for different applications. And if you compare that with traditional lighting solutions, you find that the LED is at least as good, if not better. So then we come back to the important question, which is cost. Why aren't we already doing this? And at the moment, the picture looks a little bit like this. This is comparing it with parking lighting or street lighting. It would be pretty much the same. So it is more expensive at the moment, but that's largely because we're just at the bottom of the curve in terms of supplying volumes. So if you look for the total cost of the light fitting, including the light source, then it's around a factor of 2 more than the more traditional solutions. But then, of course, the lifetime is also twice as long. So if one were to look at the cost over lifetime, then it's actually already comparable to today's solutions. Of course, not all applications are interested in these kind of lifetimes. You know, if you put it into your house, the fact that it would last longer than the amount of time you're going to live in your house is really not too interesting. So, but costs will certainly continue to come down. The last factor is perhaps reliability. We spoke about being a very reliable technology, and there are all kinds of standards to actually establish, well, just how reliable are LEDs. And the way they're characterized is to determine, well, at what point has the total intensity from the LEDs decreased by 10%. So typically LEDs don't fail completely, they fade over time. Which is again a difference to a light bulb, which tends to go bang and it's dead. Graceful failure, as they call it. And Cree's worked a lot on this, trying to identify the right kind of lifetime model so people can accurately predict how they're going to use the light for different applications. So it's very reliable. Depends how warm it gets. Again, that's the difference between different technologies. If it gets very warm, then of course the lifetime decreases. But again, for most applications, you're not going to be looking at temperatures of 140, but even if you were, the lifetime is still tens of thousands of hours. So it's a very robust and reliable technology. Perhaps an important point to point out is, in fact, it's not the LED itself which determines the value. It's the system lifetime. The LED lamps themselves practically never fail, which is interesting to know. So the weak point in the system, things like optical components, the filters and things like that. In fact, the weakest element is the drive system. LEDs are a low voltage device, so you have to step down from high voltage to low voltage, and it's that conversion which actually is the weakest link. So we need to improve our power supplies and make them smaller. And then these things do get hot. As you felt from a normal light bulb, it gets hot. Not so hot as a light bulb, but it does get warm. And the heat sink is an important part of the design. So in fact, the lifetime is the lifetime of the system rather than the LED itself. So when it comes to the lifetime and improving lifetime, it's actually a lot in common with the semiconductor industry, where there are decades of work on how you establish the lifetime reliability of technology. So that part of the business is very well understood. We work very hard to make sure that this is a reliable technology. And now LEDs is establishing a new, like a new paradigm when it comes to lighting, because it becomes a non-replaceable technology. In other words, when you design your lighting fixture, you don't design it with the idea that at some point you have to get in and exchange the lighting, the bulb. The LED is going to last a lot longer than the fixture itself. So you begin to get a different idea about the use of light. You don't design it to be able to access it, to be able to replace it, but you can think about using lighting embedded into your wall. You can have, instead of a single point source in your room, you can have tens of light sources, so you create an ambient light, which is very different. So the whole way we use lighting will change when you have a non-replaceable technology. Okay, finally. I hope I've given you a flavor for the fact that now LEDs are very well established as the most efficient light source, which really is going to have a huge impact on our use of light energy in the future. So at the moment, the way that the LEDs are being developed is to replace the existing technology. They have to have the same sockets. They have to mimic existing technologies. Now, as the technology becomes more established, as I said, that won't be necessary. You won't need to have the same fixtures because you will replace the whole fixture itself. So that will change the evolution for LEDs. They're becoming more cost-effective, and because there's a greater ability to optimize for different applications, you'll see this diversion in products depending on what application they're being used for. Okay. Thank you very much.